Okay, next example is how you can find the equation of modulated signal YT and also the message signal MT, or modulating signal. So given in the example here is a figure with signal XT and also the carrier signal, already given the equation here, CT equal to cos 160t, and as the this is the modulating or demodulation process actually can be done, and the output will be represented by YT, and it will pass through a low pass filter with a gain of 2, and also the absolute value for angular frequency is less than 100. Okay, and you will get the message signal at the output. So what is what we call it, this YT equation and also the MT equation, if actually we can have a equation from XT. Given in this question is actually an equation using capital X omega. So you need to do some conversion in using Fourier transform, because we have angular frequency here to be converted back into time domain equation. So first you need to know what you need to do is getting that equation. All right, so we have this equation here. So you need to refer to the transform Fourier transform pair. All right, whereby we have actually can translate this and also the others three components of equation here using this pair, sine omega 0t is actually equal to j pi in bracket delta omega plus omega naught minus delta omega minus omega naught. Okay, for the sine, and for the cos is actually almost similar. It just no j there in front, only with pi delta omega plus omega 0, and you need to add here delta omega minus omega 0. Okay, so having that, you actually can convert using that pair. So this one is actually become this one you can use the cos one because it's having plus over here. So this is plus, and for this one we actually can use this one, this equation, to match with sine our cos, but because we have plus over here, so we will use cos, become cos 190t, and this one is cos 196, 160, and for the next, the third component of the equation, we have omega plus 130, and we have plus over here, so we need to use cos again, and it become cos 130t. So now we have already the xt over here. So how we can get the yt is by having this xt equation to be multiplied with the ct, the carrier signal. So when we have that, ct here is actually cos 160t. So all component of this equation will be multiplied with cos 160t. So 160t. So when we have this, basically you just need to add it up. So 160 plus 160 is 320, and then you need to minus it so that you can get cos 0. This one also you need to add and also minus, so that the addition will result with cos 350, and the minus will be cos 30t. Okay, how we can get this quarter is because you need to refer to the trigonometry identity. Okay, and for the 130 and also 160, you need to add and minus, and you will get almost similar one. Okay, so rearrange this equation, you will get this one, the final line of equation, and you will see that for each t here, we have 30t, 290t, 320t, and 350t. So you need to try to sketch the graph here. So we have 1 meaning that you have this one until 2 pi. Alright, this is 1. And you have 30t positive. Alright, so this is 30 and it's actually having negative half. So you need to put it down under negative area of amplitude and so on. Okay, so this is actually the spectrum. Spectrum. So that it has, for this area is USB, this one is for LSB. Right, next, okay, so next you need to find the message signal. So just now what we have here is, this is the YT equation, okay, for the first one. And next is how we can get the message signal, because that YT must pass through the low pass filter with the gain equal to 2 and allowable frequency, or some books say or call it as cut off frequency, must be less than 100. So from this equation, actually whatever we have more than 100t is considered to be eliminated by the filter. So it will just only give you this one, 2 minus cos 20t, 30t. So but in YT is actually 1 minus how much? Half minus half cos 30t. And how come this empty become 2 minus cos 30t? So you just need to eliminate this half in the equation, and this become 2. That's why the empty become this equation. Okay, so I hope that you understand this, and when you have the empty equation, you can always sketch the spectrum here. Okay, so we have 30 pi, this is t, 30, and we have the amplitude to be negative pi. Alright, and you have to need to reflect on the same area, and 2 actually is the this is for the 2 value over here, and this is the cos 30t the spectrum. Right, next is the sampling. Actually, when we have the signals, the continuous signal or analog signal is actually need to be sampled if we want to convert it to be discrete signal, or sometimes we call it as digital signal. So how we can do that is by having the analog signal to be sampled as strain of impulses, alright, like this. Okay, so to convert the signal from continuous signal or analog signal to be the digital signal, you need to have what we call as sampling. Alright, so this sampling will make or will convert the analog signal to be in the discrete time or discrete style of signal. Or most of us call it as digital signal. So we need what we call as sampling interval, that is represented by TS, T for the interval, S for the sampling, or what we call as sampling rate. Some books say sampling frequency, which is using symbol Fs. Or we can actually relate the sampling interval and also sampling rate by using this equation 1 over Ts. So the sample signal GT, meaning that this one that already been sampled to be trained by using train of impulses, will result with it will resulted the digital signal from the analog signal. So we have GS here, okay, meaning that the sample signal, which the GT over here is perhaps it's the analog one. Alright, and you need to convert it to be in frequency domain. So will be something like, we become from the GT to be capital G with the S subscript S for sampling, and also from T become omega. Okay, so here is the place that you need to apply the Fourier transform knowledge, just what you have learned before this, into this situation. Okay, so basically we have this equation for the time domain or analog signal, and you need to know how to change them into Fourier transform by having by changing it to be this equation. Oops, sorry. Okay, so sampling cannot be done just like that. It actually has some sort of rules. So in order to ensure optimal recovery of the original signal, okay, the sampling frequency must be at least twice the highest frequency used in the as the modulating signal. So we having these rules to be used, and the sampling frequency or what we call sampling rate must have or use this what we call Nyquist rate. Fs equal to 2W. So W is the higher frequency used in the modulating signal, and we can change that to be in Nyquist interval by having the twice highest frequency of the modulating signal equal to 1 over Ts. Okay, and for example, we have these questions. Given audio signal is band limited 12.5 kilohertz. Alright, band limited. So find the maximum sampling interval. Make sure that you read it properly. The questions want the sampling interval. So using the Nyquist interval, Fs is more or equal to 2W. So W here is 12.5 kilohertz. Which is actually equal to when we times 2 equal to 25 kilohertz. So now we convert it to be in Nyquist interval 1 over Ts more than or equal to 25,000. So you need to do some basic calculation here. So Ts or in Nyquist interval here is actually must be less or equal than 40 microsecond. So that you already know that in order for you to get the optimum optimum effect on the recovering information signal, you need at least 40 microsecond as the sampling interval. Next, for the next example, we have the highest frequency of a voice signal 3.4 kilohertz. So what is the sampling frequency that you need to set to change from the analog signal to be in digital signal. So for the Nyquist rate of the sampler, you need to find it twice of the highest frequency. So 2 times 3,400, you will get 6,800 equal to 6.8 kilohertz. So just simple as that. Okay. Another type of question that can be asked in asking you the sampling of the sampling setup you need to be done in this by giving you an equation, and you need to find what is the omega here, because we want to find it we want to find the Nyquist rate and also Nyquist interval. So here from this equation, you know that omega is actually the sine is omega t, sine omega t. So omega here is 200 pi, and from here you can find what is the frequency of the signal by having the frequency equal to W. So 200 pi divided by 2 pi, because this is the T, right? This is omega, so become 100 hertz. So in order for you to get the Nyquist rate, you need to times 2. So 2 times W, you get 200 hertz, and you can convert that to get the Nyquist interval. So when you do this calculation, you will get 5 milliseconds. So you need at least 5 milliseconds to be set in order for you to convert the analog signal to become digital signal for the sampling. Okay, so I think that's it for this chapter. As conclusion, I hope that you already know how to determine the Fourier transform using the table and also the properties I already explained in the class, and also determine the Fourier transform using derivative technique, as well as how to get the inverse Fourier transform that can be transformed from the signal in the frequency domain to the time domain, as well as how to apply the Fourier transform in the real applications, such as in having amplitude modulation signals. So I hope you can understand and try to use some tutorial questions given to make you understand better of this chapter. Okay, thank you for listening. You may contact me anytime for the further clarification. Thank you.